Thank you very much. So hello everyone. So yes, I'm Martin Ray. I'm a researcher at the university in Lund, and I'm kind of new to Sweden in general. I arrived last year, so it's a pleasure to present some of my research and some of the topics that are close to my heart to you. And yeah, today I would like to take you through one of my favorite journey in science. And it basically starts from a very simple question, and that is, what is our universe made of? And if you start looking around you, you might start by saying, well, our universe is made of chairs and tables, or rocks and forests and everything we see on Earth. But if you keep zooming out, you'll really quickly start seeing something like the sun, and that dominates the mass that we see in the solar system. So that's our sun right here. And it wouldn't take long before one of you finds their way to a very beautiful night sky in Chile, and what you see from there is a picture like this, where every single dot that you see is another star very much like our sun. And if you look even more carefully in the center, you see this kind of arc in the middle, and that's what we call our Milky Way, or Vintergatan in Swedish. And so that's our own galaxies. And actually our Milky Way is made out of billions and billions and billions of stars like our sun. And it doesn't stop there. We can keep zooming out. And if we use one of our best telescopes, like the Hubble Space Telescope, we really quickly realize that our own Milky Way isn't so special, that there are actually many other galaxies like our Milky Way around, like this really pretty spiral galaxy that was imaged by Hubble in the 90s. But actually there's many types of galaxies. This is the so-called sombrero galaxy, or these two galaxies that are about to collide with each other and merge together. And again, it doesn't stop there. If we point the Hubble Space Telescope to this square in the middle, and I really want you to understand how small this square is, and so I've put the moon next to it to scale with this. So I assume that most of you have seen the moon in the night sky, and that's the size of the square is on scale compared to the moon. And when we point Hubble to it, we get a picture like this. And every dot that you see in this picture is a galaxy. And each of these galaxies is like our Milky Way, made out of billions and billions of stars, each potentially with planets, each potentially with stuff on it, like humans, desks, chairs, rocks, and so on. So what I really want you to take home from this is the scale, right? Like everywhere we look, we see galaxies that are made of stars. So we can come up with a very simple answer to that question. Our universe appears to be made of stars, which are themselves making galaxies. But a quick word of caution, which is that appearances can be very deceiving, and what you see is not always the full picture of what's out there. And a quick way to be reminded of that is your own hands. What you see when you look at your hands is the hand on the left with the skin on. But if you look at it at a different angle, or if you look at it in a different light, for example, in X-ray, you see that there is a whole bunch of structure that are your bones and your skeleton below the skin that you couldn't see. And the point I want to make from this is that when we look at this picture and we see all these galaxies, we can very naturally ask ourselves, is this everything? Is our universe really made of just the stars and galaxy that we've observed? Or are we missing some of the skeleton and bones that are behind it and we have not yet seen? And the answer, I'm going to break it to you really quickly. The answer is, yeah, no. The universe is not made of stars and is not made of galaxies. And actually, the matter that we know, stars and galaxies and us, which we call atoms, they only make up 5% of our universe today. So 95% of our universe is something else. 25% of it is what we call dark matter, and 70% is what we call dark energy. So two different dark components that make up nearly 95% of our universe and that are not what we actually see with our own eyes and our telescopes. And so today, the talk, what I would like to focus on is how do we see this invisible dark component? How do we detect dark matter and dark energy? And how can we be so confident that basically 95% of the universe is not what we know and understand on a day-to-day basis? So in order to kind of explain this to you, I'll have to introduce one concept, and this will be the one and only piece of math in the talk. So astrophysics is a very mathematical subject sometimes, but I promise this will be the only piece of math. And it's about the gravitational force. So the point is that so gravity, the equation you're seeing here is Newton's law, which Newton's allegedly came up with receiving an apple on its head. And it's the fact that two massive bodies attract each other gravitationally. So the force on the left is proportional to the masses of the body, M1 and M2. And the best way to really understand how gravitation works is to look at the planets in our solar system and how they evolve around the sun. So in our solar system, the sun is the biggest mass. So actually it's attracting every other body towards it, following the law of Newton. And that's the arrow I've drawn here. However, each of this body is actually turning around the sun as well. And it carries what's called an orbital velocity. And if you combine these two arrows together, the fact that one of the body is moving this way and it's being pulled towards the sun, what you get is this green arrow, and the fact that Jupiter, for example, goes from the position that it started on the left to the bottom one. And if you keep doing this over and over and over, you end up with Jupiter being on a circular orbit around the sun. And this is very much what we observe. We observe that planets, because of the gravitational force, orbit in circular orbits around the sun, each and every one of them. So you might be thinking, well, where am I going with this? And where I'm going is that physics is actually never so simple. And I said that the gravitational force is actually every massive body attracts every other massive body. So the sun dominates the budget. But for example, if we take the example of Uranus here, it's mostly attracted by the sun, but it also feels the attraction of all the other bodies around it in the solar system. And actually, we can turn this around and say that something like Uranus would have a quasi-circular orbit around the sun, and the anomalies in the orbits carry some knowledge of how many other masses there are around. And if you are a mathematician from the 1800s, like Urbain Le Verrier, you can actually compute what the orbit of everybody in the every massive body in the solar system should be, and realize if you do the math that the orbit of Uranus doesn't actually match what was observed for it at the time. And actually, when Urban did this math, he quickly realized that the only way to explain the orbit of Uranus was to invoke an extra body that had not yet been discovered. And he went to the astronomers at the time and said, if you point your telescope right here on this day, you should see another planet, because otherwise the orbit of Uranus doesn't make sense. There needs to be an extra mass. And this is how we actually discovered Neptune. Neptune was the only body in the solar system that was discovered through math and equations, rather than direct imaging by telescope. And what I want you to take away from this anecdote is that because of the way gravitation works, we can actually predict the existence of an invisible mass from its gravitational effect on the visible mass. In this case, the invisible mass was Neptune at the time, and the visible that we knew was Uranus. And this is basically, we repeat the same experiment. If we repeat the same experiments in galaxies, and we look at how stars are turning within galaxies, so very similar to the planets turning around our solar system. And we do that at different radii, like the arrows I'm showing here. what we get is this black curve. So you see the black points that follow a line. These are the measured velocities of the stars. So how fast the stars are turning within a galaxy. And the yellow curve that I'm highlighting here is the velocity you would expect from all the mass that we see in the galaxy. So what you observe from that is that so we expect stars to be turning at the yellow velocity, but in practice they are turning at the black velocity, and that tells us that we are missing velocity. And in the same way that Uranus needed Neptune to explain its rotation, we actually need to invoke the purple area, which is an area of missing velocity and missing mass, to explain how fast stars are turning within galaxies. And this missing mass that we do not see, but that we observe because of its gravitational effect on the stars that we do see, this is what we call dark matter. So the dark matter is a matter that is out there and that we observe through its gravitational effect. And actually, when Vera Rubin did that across many galaxies in the 70s, she quickly realized that every galaxy showed this pattern, that every galaxy show this missing mass and was embedded in a halo of dark matter. So you can picture the disk galaxies that I showed at the beginning embedded in a kind of spherical blob of dark matter around it. And so this was very much the first piece of evidence that we had for dark matter. And if we come back to this picture, then we've again answered it, right? Like we've again said, well, there are galaxies everywhere. Every single one of these galaxies is embedded in a dark matter, in a halo of dark matter. So now the universe is made of some fraction of stars, galaxies, humans, and atoms, and some other fraction of dark matter. But actually, I said at the beginning that dark matter was only 24% of the entire content of the universe, and that there was this other dark energy thing that was out there that made actually the majority of our universe. And so in the second part, I want to give you some sense of how we actually know that dark energy also exists, that the universe is even weirder than weird, that we need both dark matter and dark energy in order to explain it. And for this, I'm going to move from what we call astrophysics, so the science of stars and galaxies, to what we call cosmology, which is the science of the universe as a whole and what makes up our observable universe. And you can think of this as galaxies are now becoming points. We are studying how they are distributed, how they map in our universe as a whole. So this really became a scientific field starting in the 90s, 2000, especially with the Sloan Digital Sky Survey, because it was able to actually image and map the positions. Ooh, all right, let me turn on the light again. Wow, apologies for this. This automated light is very annoying. But the Sloan Digital Sky Survey was able to map millions of galaxies and to map their position across our universe. And again, I want to take a quick moment to really make you understand the scale of what this means. So this is a movie that was made with the data of the collaboration. And every point you see in there is a galaxy that was imaged by the Sloan Digital Sky Survey at its correct position in our universe. So once again, each of this point is a galaxy. Each of this is made of billions of stars, potentially with dozens of planets around them, each potentially hosting life. And I always find it kind of breathtaking, even myself that works in this topic on a day-to-day basis, to be reminded of how huge the universe actually is and how many galaxies and stuff there is out there. And that's actually, so this studying, so if we compress this movie into an image, this is what we get. So each point that you see here is an observed galaxy from the Sloan Digital Sky Survey. So we sit at the center, and you see that our universe is very special, right? It's not random. There's a lot of structure in the distribution of galaxies. So you see something that probably reminds you of a spider web. You see places where galaxies are clustered together, where thousands of galaxies are in a very small confined space. You see places where the galaxies are along elongated filaments, or places that have no galaxies, that are voids. And studying this structure, studying the web-like structure, the cosmic web, what we call the cosmic web, is actually what I do as part of my day-to-day research. What I focus on is actually to recreate the structure of the cosmic web on my computer. So what you're now seeing is a movie I made out of a simulation I did of the universe, because nowadays we can fit the universe in a laptop. And what you see is very similar patterns. You see places where there's a lot of matter in one place. You see filaments, you see voids. And we've become extremely successful at recreating this structure. But because it's on a computer, I've actually cheated a little bit, because what you're seeing here is actually the dark matter component of our universe rather than the galaxies that we were observing before. Because everything is digital, I can actually show you the dark matter rather than showing you the visible like in our real universe. And you can think of as the cosmic web just like a Christmas tree. So when it's dark, you mostly see the lights on the Christmas tree. And in our case, the lights are the galaxies. But because of the way the lights are distributed on the tree, you can actually guess that there is a structure behind it, that there is a dark matter web behind the lights that you can actually see just from by observing how they are distributed on the tree. And actually, if you look at different trees and different light distributions, you might make different inferences on the background tree that is hosting the lights. In our case, the dark matter cosmic web. And that's basically how we know about dark matter and dark energy. We take the observed cosmic web from the Sloan Digital Sky Survey, and we try to reproduce it on a computer. And so that's, for example, one guess I did over the weekend, actually. And you see that in this case, the simulation doesn't really look like what we've observed. And that's because I've generated a cosmic web with too little dark matter in our universe. I can make another simulation that starts to look like what we've observed, but is still not quite the same. And that's because I've now put the right amount of dark matter, but I haven't put the right amount of dark energy in my computer. And actually, if I want to reproduce the observed cosmic web, I have to put the exact right amount of dark matter and the exact right amount of dark energy to match the observed cosmic web from the Sloan Digital Sky Survey. And this is how we are so confident, how we are so confident about the existence of dark matter and dark energy, that the universe is even weirder. We needed dark matter from observing galaxies, but from observing the cosmic web, we've realized that we actually need both. And that the structure of the web actually allows us to infer how much of this component contributes to our universe. And this is how we end up with a picture like this, with a picture where 5% of the usual matter, us, suns, stars, planets, make up the universe, and the remaining 95% are made out of dark matter and dark energy. Okay, so this is a pretty fast talk. So in the remaining minutes, you might find yourself a bit suspicious, because I've only had the time to mention 2 lines of evidence. And if you've ever done sailing or boating, you know that 2 lines are never enough. So if you're in a sailboat on your way to Loma Harbor and you want to know where you are, you, for example, can take the angle from turning torso against the boat. and take the angle from the Loma Tower against the boat, and the intersection of the two lines give you where you are. But in practice, the boat is moving everywhere. You're not perfect in the way you're measuring your angles and so on. And you end up with a picture that usually looks more something like this, where your two lines intersect, but they actually do not intersect at all where your boat is. And that's why you take a third piece of evidence. You take a third line from the nuclear power plant, for example, and you don't know exactly where you are, but you know that your boat is within this triangle of uncertainty. And we've gone through a very similar process today, because I've shown you one piece of evidence that our universe is almost entirely made of dark matter and dark energy. And that was the rotation of stars within galaxies. I've showed you a second piece of the structure of the cosmic web, coming from the structure of the cosmic web. But what I really want to stress is that these are not the only two. And actually, to mention a few, the cosmic microwave background, which won 2 Nobel Prizes for both its discovery and its characterization, or the dimming of supernovae, which was also awarded a Nobel Prize. And some other, actually many lines of evidence points towards the same answer. We have many ways to test that our universe is made of dark matter and dark energy. And every time we do, the area of uncertainty shrinks, and we become more and more confident about this statement. So the point I want to finish on is that we now have many lines of evidence that our universe is primarily made of two invisible substances, dark matter and dark energy. But this is not actually the end of the story, because to come back to the Christmas tree, what this tells us is that there is a tree, but we still don't know what the branches of the trees are made of and what the leaves of the tree are made of. We still don't know what dark matter and dark energy are. We can see that they are there because of their effects on the visible structures that we observe. But it really remains one of the biggest open questions in modern physics to understand the nature of them. And it's actually one of the reasons I joined astrophysics, is because of how exciting I find this as a challenge. And it's for the next probably 10 years, 20 years, if maybe shorter if we're lucky. So to me, this is one of the biggest problems that we have in modern physics, pinpointing the nature of dark matter and dark energy. And I'll stop there and take any question you have now, or you can also contact me by email if you wish to discuss this further. Thank you very much for listening.